All right, so we're ready to start. Before we introduce our next speaker, I'd like to have Gary Grider from Los Alamos National Labs. He's going to make an announcement for a plug fest that he's working on.
Hi, so I'm Gary Grider from Los Alamos National Laboratory. I've been trying to get PNFS to become a thing since 2002. So 2002, I started funding what became PNFS. And PNFS is starting to become a reality. There's multiple offerings, Hammerspace, Pure, and others, and there's actually a couple of open source ones being developed. In order to support that effort, because PNFS is a scalable thing, there needs to be a scalable test bed for people to try out, because not everybody's going to have 1,000-node clusters to try out PNFS on. So I'm funding an effort at Carnegie Mellon University at the Parallel Data Lab to put in multiple hundreds to thousands of node test clusters to do PNFS test and evaluation. So if you're a company that's selling a PNFS solution, you can take it there and try it at 1,000 kind of node scales and 200 gigabit kind of things. If you're an end user and you want to say, if you would only run this test and tell me if it works, I might buy it. You can do that there too, or you can ask us to do that. It'll be public. It'll be completely open. There'll be a website that says, here's what we've run. Do you want us to run any other kinds of tests for you? And so the idea is to foster the PNFS community to get the ball over the damn line so that we're done with it. And 2002 is a long time ago, right? And so we've been at this a really long time. So it's time to get the ball completely, all the way to the end goal. So anyway, that was all I wanted to say was we're doing this. If you're interested in PNFS, this center is going to be available to the public at large, essentially, to guide where it goes, and the companies that want to try solutions can try them out there. Thanks.
And if you're curious to learn some more history on that, actually coming this Monday is a podcast featuring Gary talking a little bit about that and the history of what Los Alamos has driven from our friends at the Futurum Group on a Utilizing Tech broadcast. So up next, we have Curtis Ballard. There you go, I screwed it up. Curtis Ballard, he's a technologist at Hewlett-Packard Enterprise in their storage group. If it has stored a bit, he's probably worked on it in the last 20 years at HP and HPE. He's going to come up here today and talk to us about storage for AI. So.
Thanks, Scott. Yeah, I had to chuckle a little bit this morning. I don't know if any of you guys looked at your printed agendas. This is NAN overview of AI workloads for storage on your printed agendas. Not a number, but for AI, we have to take all these things that are not a number and make him a number so we can work with them. So it's almost backwards where we really should be. So I'm going to try and give you a quick introduction to what AI workloads mean for storage. So let's see if this... Okay, and here's a quick intro to your speaker. We had two possibilities for speakers today. Turns out one of them was AI generated and we couldn't get him to show up. So you're stuck with me, as you said. I'm with Hewlett-Packard Enterprise. This talk is primarily presented on behalf of SNIA and the SNIA Technical Council. I work with the SNIA Technical Council, which oversees the technical work of the SNIA organization. I'm one of the co-chairs on a group sponsored by the SNIA Technical Council that is looking at how SNIA can help support the AI storage industry. And so today we want to give a little bit of a very, very high level. We don't have all that much time, so we're going to try and do a high-level introduction to storage for AI that can be a foundation for other AI presentations. We can't get very deep in this, and really, this is thinking food for planning storage for AI. You're not going to be able to design a storage system for AI with the depth of information we can go into today, but you can get you started thinking about what storage really means for AI. But what kind of storage? When we talk about storage, is it memory? Is it persistent storage? Well, we're going to focus mostly on persistent storage, almost entirely on persistent storage. There's a ton of memory usage too. We can't get there today. But for persistent storage, is it file, object, block? Is it direct attached? Is it SAN, NAS, external? Like anything with AI, it depends. We're going to just cover the general characteristics of the perspectives from the storage. Some of the things in here are best served with file or best served with object, depending on what you drank for your beverage this morning with your breakfast. Block storage fits in other places. So the specific storage implementation for any given workload has a lot of choice points, and you'll have to design your specific storage, but we'll try and cover a few general characteristics. One of the key things that got overlooked early on, I don't think we need this slide quite so much anymore, but storage really is a key part of a solid foundation for an AI ecosystem, for an AI infrastructure. It's a little bit old. These numbers came from an IDC report on future-proofing hardware for artificial intelligence. It was dated August of 22. But it's still true that storage is a critical part of your AI foundation. The thing I think was really interesting about that report was 77% of companies with AI in production wanted to upgrade their storage. They had it running. They knew they needed more storage. The number I see quoted most from this report is the bottom one. If you're evaluating AI, you're planning to upgrade your storage. But the people that already had it needed it too. So this is kind of a little mini agenda type thing. We're going to talk a little bit today about why is storage for AI different. Some of the key things are it requires huge quantities of data, and different quantities, different data in different phases. It does extensive data manipulation with different types of data manipulation in different phases. And it's a multi-phase workload. That's a very unique characteristic that's different than some of our traditional workloads that have been a lot more predictable. And its performance and capacity needs vary widely across different AI tasks. And then you've got highly parallel operations. We've dealt with all of these things in isolation before, sometimes 2 or 3 of them. We're finding that dealing with all of these things in the exact same pipeline is quite an interesting adventure. So what is data? Data is food for AI. How has that changed over the years? This is a little infographic here to remind us that AI runs on GPUs and CPUs. That gets a ton of attention, but it eats data, and the data eats storage. And that data has been exploding from gigabytes of data back in the days of early days of speech recognition, building off of traditional AI that didn't use tremendous amounts of data, up to where now we're using petabytes of data for reinforcement learning and generative AI. And it's just continuing to grow. So you have to keep your AI fed, and that food is your data. And your data has to come from some storage. Most people, I think, have this by now. There's really 2 sides of AI that get all the focus. And they're really the key phases of AI, your model training and your inferencing. I don't think we need to talk about this too much. Your model training, you try and take all your unstructured data and you feed it into a magical process that's your IP and build a trained model. You put your model over into the inferencing side where you feed your production data into it, and you try and generate business value out of the bottom. All the time in a circular loop here, updating your training data set from your inferencing and updating the model to keep putting more powerful models into your inferencing all the time. But there are several phases behind those that are critical to understand in the respect to your storage. So here's a nice fancy AI generated. No, not really. Be a lot prettier if I used AI, but where's the challenge in that? So this is kind of a perspective from the storage side on where do we see differences in workloads for an AI pipeline. With your data ingest over on the left-hand side here, some of your production data, some of your traded data, going through a pipeline of data cleaning to data preparation, to the model train that gets all the attention, model eval and tuning, and then over to the inference side where we're seeing a lot of the attention is shifting to the inference where you get to generate your business value. And over there on the far right is what we call our ugly stepchild. This is the data archive. Don't forget, you have to have a whole pipeline there. I think it's interesting at the September SDC, the archiving sessions were very lightly attended, and then in the AI sessions and in the hallway outside, there was a lot of conversation about, but gosh, we're building up problems of creating all this data that now we've got data we have to store forever, and we don't know how to do that. So I think that piece over there is interesting, even though it's kind of neglected today. So AI affects all of your storage, and we need to think about storage needs for today and tomorrow and how AI changes those requirements. So let's start looking at things. So this is kind of just an example of one case of how you want to think about how AI affects your storage ecosystem. For this example, I'm using data ingest. Everybody's business has a data ingest system today. They've got their business systems running, the data, they're generating data, it's going onto systems, we're all set. We have that storage, right? Well, is it the right storage? We don't know yet. The business data is being captured, but AI can affect what you capture, how you store it, how you use it. So there's a lot of different effects to it. This was brought to really interesting point for me. I met somebody just in a general conversation over dinner one day, and we were talking about what's your company do, what's my company do, and they were telling me about their company is a company that has a lot of different manufacturing sites. They manufacture a huge variety of different things, and he was telling me about his biggest problem of the day was that his company had done some evaluation on AI. They had a business process where their production data was generated, went into some business logic, and they generated some key measures off of their business logic and discarded huge amounts of data. A lot of this is just log data, production line setup, teardown records, logs that were captured while things were running. They kept key points and threw everything else away. They ran some AI routines on some of their data and discovered that they could get really interesting business insights off of data that they had been discarding. Reviewing manufacturing setup data compared to the production runs helped them figure out where there were things that had happened in the setup that made the production runs run better or worse. And they were losing this data, they were throwing it away. So his current problem was their data ingest system was completely wrong for where they went to take their company. They needed a system where they could do enhanced business logic with AI on their data ingest. Then they wanted to figure out some way to do a data valuation AI, figure out what they need to save, what they need to throw away, and they were finding it hard to throw any data away. They needed to build an entirely new system to create a massive data lake to store data that they used to think wasn't critical to the business. So that's just one example. AI disrupts your business all over the place. So let's take a quick look at what the storage requirements look like for the different phases here. So the first one in the diagram up there at the top right, I've tried to show where each of these are. I called this phase the data aggregation. This is really your primary data ingest. This is where all your raw source data comes in. You have to prepare it for use in AI. Could be logs, pictures, videos, documents, etc. Whatever, mostly unstructured data, and that all needs to be organized before it comes training data. A bunch of different things you can do. You can clean out the noise, deduplicate, normalize it, do your privacy ethical processing, etc. So you read your data from your ingest storage, you run your operations, clean that, and then that data is written over into a data preparation phase. Some people are trying to automate this. Really, the ideal, I shouldn't say some, everybody really is trying to automate this as much as possible. So over here on the left, I've tried to create some little diagrams to kind of give you an idea. Your data ingest or your data aggregation phase, all of the data comes into there. So capacity, you need a full pie. Your write performance and the read performance, those aren't generally the most critical things in this phase. With your write being a lot of sequential data being pouring in from all of your production data perhaps, tends to be highly sequential with a little bit of random. Read performance, your read has to be a lot random. So that's the data aggregation phase. Then you get to the data preparation phase. A lot of things I've seen combine these two. The data preparation phase is where you're taking your data scientists, they're serving as translators, taking your raw data, converting it into food for AI. Really is numbers, not a number, isn't applicable there. They have to explore the data, identify patterns, outliers, relationships. They split the data, they do feature extraction, data transformation. I say often highly parallel, virtually always highly parallel. This may be able to be done together in your same data storage system for the ingest data, but the workload that the storage system sees while the data preparation is going on is very different than the workload that the storage sees on data ingest. So is it the same storage or a different storage? It depends. Capacity, you don't need quite as much capacity. You've filtered out some of the data. Yeah, your write perf, read perf, you actually need more write perf, read perf in most instances in this phase than you did in your data ingest phase. And these tend to be almost all random, very random, not a lot of sequential. So then we start moving into really interesting stuff. I've got a little bit more content here on the model training. There's way more than we can even begin to scratch the surface on here. But where does storage play into model training? Model training, the really fun stuff, the model training uses memory. It's not using the storage systems during the key training pieces. The storage ends up primarily being used loading the memory for training and getting the data out of the memory. The biggest piece for getting the memory out is the checkpointing. So in checkpointing, they create a point-in-time backup of the model that's copied off for recovery. When you've got a model that runs for maybe several months, if you have a fault and you have to restart, you lose a huge amount of time and money. So everybody's doing checkpointing now, running in the bigger models. So that requires some amount of pausing the GPU to grab the model state out of the GPU. And that checkpointing today tends to be either one of two kinds, synchronous or asynchronous. It used to be all synchronous. A lot of it's going to asynchronous. In the synchronous mode, you pause the GPU, you copy the memory out into CPU memory, then the CPU is responsible for copying it into some form of persistent storage, and then you restart your GPUs. That leaves your GPUs paused longer than a lot of people want, so a lot of people are doing an async model now, where they pause the GPU, get a snapshot out of memory, and then get that GPU back going to work just as fast as possible. Tend to use a lot more memory in that configuration, and periodically they'll pick a snapshot, and the snapshot will get persisted to more persistent storage, so you've got multiple levels of recovery. So that tends to be kind of the biggest piece of your persistent storage for the training phase. And what's kind of new and different in this phase, I think we're starting to see a rise of interest in fast object in the training phase, also in the inference phase, but I dropped this slide into the training phase because I think it's really interesting there. This is something I think is worth watching. Object storage is a convenient way of doing storage, but it's traditionally had a higher latency than file. So file has been the predominant type of storage that we've been seeing, especially for the training phase. But there's really a lot of evidence that fast object is gaining in popularity. And we're starting to see people talking about RDMA accelerated object for both training and inference. In fact, SNIA is investigating, there's some gaps in some of the industry specs around RDMA accelerated object storage. So there might be some opportunities or some interest in trying to plug some of those gaps there. So what does it look like for model training? Again, this is very much generality, super high generality. The checkpointing, as we said, is the interesting phase. You're pausing your training during that, and you kind of want to figure out your storage performance, really based around a lot your checkpointing goals. So your storage capacity is about middling. Write perf, there's a lot of disagreement on this. If you're doing synchronous checkpointing, you really need high performance write. If you're doing asynchronous, you really still probably need high performance write because it affects how many of your snapshots can be copied off to your persistent storage. And then your read performance, when you have to recover from a failure and you're reading the data out of your checkpoint storage, you really want that fast performance. Get it read back out of storage, load it back into the GPUs and up and running as fast as you possibly can. So how do you plan your storage for model training? That's challenging. I can't even begin to scratch the surface there. There's a link here at the bottom for a presentation that was given at a previous SNIA talk that has a lot better information about planning your storage for the model training phase. But we all know the GPUs drive the cost. A lot of work goes around maximizing the GPU efficiency. You want to design for balanced architecture, and you have to consider your data sources. A lot of it's filed today. Like I said, object seems to be gaining popularity. The thing that I think is really interesting is these last couple bullets. A lot of people don't realize it, but if you know your training workload, if you're running a specific model, different models have different storage characteristics. And if you have a known workload, you really should design your storage to match your workload so you can optimize your spend. There's a lot of complexity for how you do that. One model that really high level, you can use your AI GPU benchmarks to see what type of performance those models have. You can get some of that from ML Perf. And there's some basic calculations you can do to determine what kind of storage performance you need. We see a lot of people that are trying to build, I just want to build a general purpose AI system. And in those cases, you're probably going to have to oversize your storage if you want to support GPU max read speed. That's what you have to design for to have general purpose going to work as fast as possible in every workload. Okay, so then we get into the phase where we look at evaluating the model, tuning the model, and again, your storage requirements change. You still need high performance write and read. You have more sequential store in this type of phase, but you still got some random in there. So this is measuring how well the results of the model match your expectations, tuning the model, adjusting the parameters, and feeding that information back into the other phases of the processing. Then we roll over to inference. This is the one where we really want to be at. Inference, we're seeing inference has really high performance read requirements. In pockets, things vary, but in general, for the inference phase, think like starting a conversation with a chat bot. The system's loading a ton of data in the background to get to that first response. You want it to be as fast as possible so you don't have to sit there waiting forever for the response to come back. And so that's running your production data through the finished model, trying to generate your business value. There's lots of different types of inference, and every type of inference has different workloads on it. One of the most popular ones is retrieval augmented generation. Got just a little bit more information on that one because it is so popular. Predictive analytics is a popular model, and computer vision. We see a lot of computer vision these days. And so the patterns vary. Some of them look kind of like traditional database workloads, but they tend to be used in different databases, using vector databases instead of relational databases. And so there are some differences in how these workloads use the storage. So mention the RAG case. If you're not familiar with RAG, here's a quick introduction to RAG. Your basic large language model, you can put a query into a large language model, and the large language model can generate a text response that's based on the training data. The training data is obsolete from the minute you press go on starting the training. It's more obsolete when the training completes, and it continues to get more obsolete from that point on. So most people these days are using RAG, which is retrieval augmented generation, where you take your large language model and you also combine your business-specific data, generate embeddings off of that business-specific data, put it into a vector database, and then have your large language model that is able to augment the results of its responses based on your company-specific business data and your most recent model data to generate your text response. Another thing that is getting a lot of talk these days, I'm not sure how this one is really going to affect the storage, but it's an interesting one to keep an eye on. There's a lot of people talking about agentic AI now, and this is one that I'm trying to figure out, what's it really going to do? Is it substantively different from the perspective of the storage? I don't know yet. A lot of people are saying it's the next wave of AI digital transformation. I got that quote from one of my leads in my company. I've debated with him whether we agree with that quote or not, but then there's so it's an application of AI to perform tasks on behalf of users. It's designed to try and learn and act autonomously in complex environments. Still in the early phases. It generated a lot of excitement and activity. It's going to be interesting to see where it goes here. I say it may use RAG. There's a model called Agentic RAG, and that seems to be one of the more popular mechanisms there. It's not clear that it's always going to use large language models. Some of the agentic AI seems to be looking at very domain-specific models that are much more tuned to very specific domains and making highly optimized decisions in those specific domains. So that's going to be a really interesting space to watch. And then, as I've said earlier, please don't forget that you have to think about archive, what you're going to do with the data in the long term. In terms of capacity, archive is a whole different beast. There are regulations in some spaces around AI where all of your training data has to be saved for the life of your model. There are some regulations starting to emerge for AI use in healthcare where massive amounts of data have to be stored. So the capacity for this, the archive side of things is exploding, and I think we need to define some new technologies to help us control the costs and the size of the data that we're trying to store forever now. The write performance isn't too bad, mostly sequential. Read performance isn't too bad, mostly sequential. This tends to be really driven by just fast enough at the absolute lowest possible cost. One thing I think is interesting is that the industry doesn't seem to have come up with a term on this yet. I called it archive in these slides, but if you've been in the industry for a while, it's really not the traditional archive that we've talked about for years and years. It's got a different set of rules and use cases around it. So it's going to require some low-cost, low-carbon footprint storage. There's a couple of things going on in the industry right now that are interesting. SNIA is heavily engaged in the DNA storage research space. There's some optical storage technologies that are really interesting for this space as well. And that brings us to the end of the presentation. Hopefully it's given you a quick intro to some of the things to think about as you think about storage for AI.
Questions?
Yes, there's one back over here.
A question about access patterns. You mentioned random and sequential I/O. I think for reading, random reading, most people know what that is. Random writing, there's often different ways of doing that, small files, overwriting things. Can you highlight a little bit which type of random write is typical in these cases?
Oh, that is so much of a challenging question. Even the random reading varies. You know, I've got a bunch of data on some of the random reading characteristics. Is it random reading or is it sequential reading? It depends. There's some of the patterns that we're seeing for training. If you zoom out, they look like they're doing random reads. If you zoom in, they're actually doing a sequential read over a chunk of data, and then they jump over to another chunk of data for another sequential read, but in another random location. Is that sequential or random depends upon your storage architecture and how it's optimized. The writing, most of the cases we're seeing for writing tend to be doing writing of modified data into new locations more than overwriting existing data. But it really, I'm sorry to say, it depends.